Hi, this is Dr. Eddie Morgan over at Clovis East High School. Want to help you with the homework tonight. We're looking in Math 1, Worksheet 5.1 today. Remember that each of these problems mirrors the exact problems on your homework. So if you're having trouble with a particular homework problem, fast forward to that problem and we should be able to help you out. Problem 1 has us look at a table and determine whether each table or rule represents a linear or an exponential function. The key difference is a linear is it's going to be going up by some amount. You're going to be adding a number, the same. And an exponential, when you look at them, you're going to be multiplying. So as we look here, I can see that 13 minus 7 here is 6. And look here, 19 minus 13 is 6. And 25 minus that is 6. In other words, what we have is a rate of change that's the same. And in a linear equation, the rate of change stays the same. Notice my rate of change here. Between 1 and 2, I have 13 minus 7 over 2 minus 1, so I get 6 over 1. If I go to the next one, I have 19 minus 13 over 3 minus 2, and I get 6 over 1. And finally, I have 25 minus 19 over 4 minus 3, 6 over 1. I have a constant rate of change. It has a common, sometimes we call this also a common difference. You remember that from our sequences. And so when you have a constant rate of change, this means you have a linear function. So the first one here is a linear function. Problem number 2 is like number 1. Once again, we're trying to determine if it's linear or exponential. Linear means it has a common difference. It adds something each time, the same number. Ratio means it's being multiplied by something. Now, when I first look, I look here and say, does it add something? Well, from 40 to that is plus 32. But notice the next one here is 160. So that tells me this is not linear because I'm not adding the same amount. So let's check the ratio. So my ratio here between the first two is 40 over 8. 40 goes into 8 5 times. My ratio in the second one, 200 over 40, which is again 5. And then lastly, 1,000 over 200, which is 5. In other words, what's really happening here is I am not, and let me just erase these for a moment. I am not adding here. I am actually multiplying by 5. That's my common ratio. Okay? And when you have a common ratio, in other words, this next term divided by the previous term, and the ratio stays the same, or you can look at it as each time I move up 1 here, I multiply by 5. Move up 1, I multiply by 5. This tells you you have an exponential function. Okay? In problem 3, we're again going to determine whether it's linear or exponential, but this time we're going to look at the rule. Now, if you remember what the rules are, a linear function looks like this. Y equals some number x times x plus b, the y-intercept, whereas an exponential looks something like this. Key thing to notice here is here, the x is in the exponent. Here, it's down here to a power of 1. That's what we're looking for. When I look here, I notice here my x is in the exponent. So the x is in the exponent. And notice it has that form. Y equals a times b to the x. There's the x, there's the x. So this tells me this is an exponential function. Problem 4, like problem 3, once again, we're looking to see, is it linear or exponential? We're given a rule. Remember our rules. For a linear equation, it's y equals mx plus b. M is in the first order, meaning mx, or you could put a 1 there, mx to the 1 power. They're the same. While as an exponential looks like this, where the x is actually in the exponent. Now, if I notice here, x is right here, I could multiply 3 times 4 and end it with this. In fact, I could even say there's none. I could even add this and say, okay, this is 12x plus 0. So notice it fits into this pattern. It's a linear equation with a slope of 12 and the y-intercept is 0. So this would imply by the rule that this is a linear function. Problem 5 is much like problem 3 and 4. We're being asked, is it linear or exponential? Again, what does the standard rule look like? For a linear, it is y equals the slope times x plus the y-intercept, mx. Notice x is to the first power, although we often don't put the 1 in there. The exponential, on the other hand, is distinctive because the x is in the exponent, see? So when I look at this equation here, y equals 7 to the x, it looks more like this one. I mean, I could write this way. I could say 1 times 7 to the x, adding that 1, and you can see it matches up with a times b to the x. Key is x is in the exponent, and so this is an exponential function. Problem 6 asks us to find the average rate of change for the function f of x equals minus 5x plus 12 over the interval 0 is less than or equal, x is less than or equal to 2. Now the average rate of change will remind you very much of the slope formula. Average rate of change, if I'm going from A to B, looks like this. I find what f of b is, the function defined at b. I subtract what the function is at a, and then I divide it by b minus a. So in our case here, we're going to have f of, let's just find first of all, f of 2 is going to equal minus 5 times 2. Notice I put the 2 in there, plus 12. So that's going to be minus 10 plus 12, or it's going to be 2. Meanwhile, f of 0 is going to be minus 5 times 0 plus 12, which is going to be 0 plus 12, or 12. Now, using our formula, I'm going to have, the formula actually then is f of 2 minus f of 0. Notice we're going from 0 to 2. That's where these numbers come from. Divided by 2 minus 0. So noticing that f of 2 is 2, I end up with 2 minus 12 divided by 2 minus 0. So I get minus 10 over 2, or negative 5. So the average rate of change is negative 5. One thing to note in particular is, notice that this is a linear equation, mx plus b, and my average rate of change is simply my slope. Okay? On a linear equation, the rate of change is the slope, no matter no matter what domain you use to find it. That's not the case with exponential functions. We mentioned in the last problem 6, when we were looking at a linear function, that the rate of change between the domain, if x is between a and b, that the rate of change is, you find f of b. What is the function here when we have b? Minus, what's it when they have a divided by b minus a, okay? Now, we noted last problem that the rate of change in a linear function is always the same and it equals the slope, but that's not the case here. So let's let's find some of these. I need to find 0, 2, 4, and 6. So I'm going to find g of 0. G of 0 equals 4 to the 0 power, and any number to the 0 power, no matter what number it is 1. All right. Now I find g of 2. This is 4 squared, and 4 squared is 16. All right. And then we're going to have g to the 4th power, and that's going to be 4 to the 4th power. So that's going to be, let me take my calculator real quickly. That's going to be 256. and then g to the 6th power, g of 6, 4 to the 6th power, is going to be 4,096. So now we can find our rate of change, all right? Between 0 and 2, that's going to be f of 2 minus f of 0 over 2 minus 1. Again, using this formula here. So that's going to be f of 2 is 16. 16 minus 1 over 2, which is going to be 15 over 2. So that's the rate of change between 0 and 2. All right? Between 2 and 4, we're going to have, what's the function at 4 minus the function at 2 divided by 4 minus 2. So in this case, we're going to have 256 minus 16 over 2. So that's going to be 216. That's going to be 240 over 2, or that's going to be 120. So that's my average rate of change. Notice that the rate of change changed. Here it was 15.5, or just under 8. It went from 8 to 20. But the reason for that is if you have an exponential function, notice here the slope would be there. But now if I move to a different spot, it looks like that. And we should expect for the next one to be even bigger. Okay? So let's look between 4 and 6. So I want to find what is the function at 6 minus what's the function at 4, and divide it by 6 minus 4. And you'll notice here that at 6, it's 4096 minus 256 over 2. And so if we subtract here, I get 0. 9 minus 5 is 4. 3840 divided by 2, which is going to equal 1920. So notice it's going significantly up. And again, I point you to this diagram up here. Notice when it's at this level, it's looking pretty level. And then we move up and it starts to steeper and then even steeper. So, and an exponential function of this nature, the average rate of change is constantly getting bigger and bigger and bigger. I do apologize for one thing here. This is g of x, and I did it right here. But then over here, I started using f of x. These should be g of x. Problem 8 asks us to tell whether each situation can be modeled by a linear equation or an exponential. Again, we're thinking here, is there a common difference? That would be a linear, meaning I just add something to each one of them. Or is there a common ratio, which means each number gets multiplied? So notice here, Ryan is leasing his car for $175 each month. Now let's consider the total amount he leases it for. Let's say he starts in January and he pays $175. Now in February, he has another one, but so what's going to happen here is he's going to add $175, okay? So his second month payment brings him up to $175 plus $175. Get this right. Brings it up to $350. And then in March, he pays again, $375, okay? I mean, he pays $175, and now he's up to $525, and you can see that each month he's going to add $175. So if each time we're just adding the same amount, we have a common difference, and so this is a linear function. Problem 9 is like problem 8. We're asked to determine whether this is a linear equation or an exponential equation to model it. Remember, a linear equation would mean that there's a common difference. between successive terms. In other words, we're adding something each time it goes up. Whereas an exponential, when you compare two terms, there's a common ratio, which means we're multiplying. Now you notice here we start with 25, and then it says it triples every month. So I'm going to multiply this by 3, and I'm going to get 75. Okay, so you should be able to see already where this is going, because notice now, what am I going to do every month? I'm going to multiply it by 3, so I'm going to get 225. So notice it's not adding the same amount, it's multiplying the same amount. So this is an exponential function. Problem 10, once again, we're trying to determine, is this linear, which implies a common difference. In other words, it goes up by the same amount each time. Or is it exponential, where we're looking at a common ratio, or it's being multiplied by number each time. This says that Drew's car depreciates 5% each year. Now, I may have to use an example to show you how this might work. For example, let's say Drew's car is worth $5,000. Well, if it depreciates by 5%, if I multiply that by 5%, which is 0.05, that implies the depreciation is $250. So after 1 year, Drew's car is now only worth $4,750. Okay, so this is year 1, this is year 2, and now what happens though is it's going to be depreciated by 5% again. So if I multiply 4750 times 0.05, I find out that that's 237 and 50. So now if I subtract 237.50, okay, I get his car is now worth $4,512.50. Now here's the key thing to notice right here. Notice that it went down, but first it went down 250, and then it went down 237, and if I multiply this by 5%, it's going to go down by 4512.5 times 5%. It's going to go, this is rounded off, is going to be 225.63. So notice it's not going down by the same amount, because each year when you depreciate 5%, the car is less worth because you less worth than it was the year before. So these amounts keep going down by depreciation, so your depreciation is going down. So in this case, each time you're seeing yourself, this is an exponential function. Another way to look at this, instead of subtracting 5%, think of it as multiplying by 95%. In other words, if you look at my example here, each time we're multiplying by 0.95. And so that's our exponential, that's our common ratio, is 0.95. All right, problem 11 is a little bit tricky. And you need to understand this concept because it shows up on one problem on the test. We're going to talk about interest and compound interest with this exponential, but this particular problem talks about a simple interest loan. Now, what a simple interest loan is that you're only paying interest on the principal. Okay? Sorry for misspelling that. So I start off with $7,000, and then at the end of the year, I'm going to pay 6%. Okay? So we multiply by 6%. That's going to be multiplying by 0.06. And you see 7,000 times 0.06. is $420, okay? So at the end of the year, I owe $7,420. Now here's what's different about simple interest. On the next year, I'm going to add 6% times just my original $7,000. So I'm going to add another 420, okay? So you notice now I have 7,840, and once again I would add 6%, but my interest simple is just on the principal, so I'm just adding 420. And notice it keeps going up by the same amount. So this is a linear function. Now, to get you prepared a little bit for this, what's going to happen when we talk about compound interest is you're going to have 7,000 plus 420 for the first year, but then you're going to multiply this by 6%, and that's going to be plus 44520. Notice that my interest went up because now I'm paying interest not only on the principal, but the principal and the interest. And this is what we call compound interest. This ends up being exponential. Whereas a simple interest, just think simple interest is going to be linear. But compound interest is exponential. All right, I hope that helped. You do well on your homework tonight.